Hi there, and welcome back to Super Awesome Calculus. Today, we're going to go over section 2.5 on continuity. We're going to skip section 2.4 in James Stewart's book on the precise definition of a limit. We'll talk about that in a second. But before we do any of that, let's look at the big problem from last week that implements some of the limit laws that we were talking about. Okay? Now, if you remember, the question was, I think I'm going to sneeze. Hold on. Alright, totally going to sneeze. I guess not. Okay. Evaluate the limit if it exists. The limit as x approaches 7 of the square root, I'm going to sneeze, wait, no, the square root of x plus 2 minus 3 over x minus 7. So let's look at this, shall we? We have the limit as x approaches 7, square root x plus 2 over x minus 7, and there's a minus 3 right here. Now, we notice right away that we can't use direct substitution, because if we do, we get, okay, 7 plus 2, the square root of that, square root of 9 is 3, 3 minus 3, we get 0. Over here, 7 minus 7 is 0. That's indeterminate form, so we can't use that. By the way, there is a very fun trick called L'Hopital's rule. If you want to learn it now, well, no, you can't learn it now. We haven't gone over derivatives. But it makes limits like these much easier. Okay. Now, here we go. The first thing that we're going to do in evaluating this limit is we're going to use the same trick that we used last time. We notice we have a radical in the numerator, so what we have to do is we have to rationalize the numerator. We have to get this radical out. And we're going to do that by multiplying by a very creative version of the number 1. So this times 1. Except it's not really going to be 1 as it is, it's going to be something that is 1. And that's going to be the square root x plus 2 plus 3 over the square root of x plus 2 plus 3. There you go. And you'll notice right there that you're going to have a much easier time at this point. So let's look at what happens. We're going to see that this becomes x plus 2 minus 9, because the 3x, this is going to happen. We're going to get x plus 2, might as well just write it out, x plus 2 plus 3 square root of x plus 2 minus 3 square root of x plus 2 minus 9 over x minus 7 square root of x plus 2 plus 3. Okay? So by multiplying by this clever version of 1 that we made up because it was convenient to get rid of that that square root, we now have something much simpler to work with, and that is x plus 2 minus 9 over x minus 7 times x plus 2 square root plus 3. Now, what we're going to do is we're going to make this even easier. Now that we have this problem broken down a little bit, we can go to limit x approaches 7, because that is what we're trying to find, x plus 2 minus 9 over x minus 7 times square root of x plus 2 plus 3. Now what happens is we can make this x plus 2 minus 9, let's bring the 9 inside the parentheses. And we get a numerator that is now x minus 7. Now what we can do is we can cancel this, and that means that we're now at the final version, limit as x approaches 7, 1 over square root of x plus 2 plus 3. Now we can use direct substitution. Let's go ahead and plug 7 in for x. We get 1 over 7 plus 2 is 9. Square root of 9 is 3 plus 3. The answer, L equals 1 over 6. 1/6. If you got 1/6, pat yourself on the back. You definitely have a good understanding of limits and the limit laws. Now, I mentioned that we're going to be skipping over the precise definition of a limit. My professor didn't really think that it was necessary to go over this, and I can understand that. It's something that will formally define a limit, but we don't really have any use for it with the material that we're going to be teaching just in this course. But in case you're curious, I'm going to write it in optional red right here. So if you're interested in what the formal definition of a limit is, it is this. The limit, as x approaches a, f of x equals L if for every number delta epsilon, delta greater than 0, that's epsilon, right? Epsilon delta, yeah. There is a number delta, and I can't, there we go, greater than 0, such that if 0 is less than x minus a is less than delta, then absolute value f of x minus L is less than epsilon. There you go. That's the formal definition of a limit. If you want to memorize it, you want to practice it, I promise you it works. We will never use it in this lecture series. So there you go. So now today what we're going to do is we're going to talk about continuity. If you remember, last time we talked a little bit about polynomials and the limits of polynomials. I used the example kind of like a parabola that at point A, if that point is within the domain, then the limit is that point. And sure enough, that is the basic definition that we're going to be using of continuity. And we say that a function is continuous if, at number A, if the limit as x approaches A, as we get closer to A, of that function is equal to the value of A at that function. So, for instance, the best way to illustrate this is using that parabola thing again. We say that the limit as x approaches 2 of x squared is 4. And it is 4. It's in the domain and it works out. If that's the case for all x, then we are continuous. So this is an example of a continuous function. What does continuity mean? Well, we'll talk about that later. Maybe not even today. Now, you might understand that there are some times when there are discontinuous functions. A great example of a discontinuous function, we talked about vertical asymptotes already. If we have this right here, 1 over x, f of x is 1 over x, we know that the limit as x approaches 0, 1 over x, well, it doesn't exist. So since the limit doesn't exist, and the limit certainly doesn't equal 0, then this is said to be discontinuous. So this is a discontinuous graph, a function, at that point. At that point, 1 over x is continuous pretty much everywhere. Yeah, pretty much everywhere except for 0. Now, these are some other interesting continuity problems that you'll see, or that you might see. These aren't functions that we're going to be really working with very much, but you should just know that things like this do happen. Here's a function, boom, okay, and then what else is going to happen? Got any ideas? Okay, yeah, that's a good one. Boom. Okay. This is a function. Now you'll notice that it's open here. We talked about right hand and left hand limits. This is pretty simple. If we're looking coming from the left, we follow the function, it's going down, it's going down, it's going down to here, but that's not really the value of the function. The value of the function is here. But we can't even say that the limit exists because the right-hand limit is going this way. Now you'll remember, if we call this point Q, what we're just saying there is that the limit as x approaches Q from the left this way does not equal the limit as x approaches Q from the right. It doesn't matter what Q actually is, the limits don't agree, therefore we know that at point Q, this function is discontinuous. However, let's look here. Let's look at point Z. Alright? Here we have point Z. Let's look at that. From the left, the limit as x approaches Z from the left does equal. It does equal the limit. They're both coming towards this same point. The limit as x approaches Z from the right. These limits agree, but we notice that there is a jump right here. That the value, if this is f of x, if this function is f of x, then the limits from both sides of f of x at point Z do agree, but you remember the definition of continuity, the limit as x approaches Z, f of x, does not equal, in this case, the value of f of z. F of z is that point. It's not this limit. So therefore this is discontinuous there at point Q. It's discontinuous and there's no limit. At point Z, it's discontinuous but there is a limit. So now you can examine different functions, right hand, left hand continuity, kind of like what I talked about with 1 over x, you know. 1 over x, if you're only looking for, if we call this point A, and we look at continuity of point A coming from the left to the right, it's continuous. It's continuous because we avoid the problem spot, 0. Now that gets us into the idea of continuity on an interval. If we say this interval, a to b, is this function, f of x equals 1 over x, continuous on a to b? Well, it looks like it because for every value of x, x is in the domain, everything from a to b is in the domain. Therefore, if everything is in the domain, then it is continuous on every point in that interval. Now, here are a few laws about continuity. These are just kind of like the limit laws. They're pretty basic. If we're assuming here that f is a function and it's continuous, and g is a function and it's continuous at point A. If that's true, then f plus g is continuous, f minus g is continuous, CF, it could be 3, it could be any number. C is a constant. CF, that's continuous. FG, that's continuous. And F over G, so long as G does not equal 0, also continuous. Very, very basic, your basic properties. You can test it. You can pick two functions. Why don't you pick x and x squared? and maybe x squared plus 3 and square root of x. Yeah. Try that out. See it, play around with it. Those are your various laws. Now, all polynomials, we basically said this, the book chooses to point out in the special theorem that all polynomials are continuous everywhere. They're continuous on all real numbers. And that's true because we basically proved before that plugging in a into any kind of polynomial is going to give you that number. It's going to give you the value of the function at that point. And a rational function is continuous everywhere that the denominator doesn't equal 0. And so when it does equal 0, that things become fun. Some functions that are going to be continuous everywhere, at every number in their domains. Polynomials, going to be continuous. Rational functions, going to be continuous. Root functions, going to be continuous. Trigonometric, sine, cosine, tangent, they're continuous at every number in their domains. Remember, if like for tangent, not every number is in its domain. Inverse trig functions, continuous. Exponential, logarithmic, all continuous within their domains. My calculus teacher for Calc 1 gave a very interesting example that he called the pathological example, which was basically a function like this. It had a value everywhere, but was continuous nowhere. It was just a series of points. And I just thought that was kind of interesting. It's food for thought. Now, with composite functions, you remember, we talked about that. FOG, fog. Things, limits and continuity generally work the same way. If limit as x approaches a of f g of x is f times the limit x of a g of x, or f of that limit. So basically, limit, this is kind of like another limit law that works with composites. Which brings us to the last and the most important point of this chapter on continuity. It's a point that we'll be using, and that is the Intermediate Value Theorem. Now, most people have heard of the Intermediate Value Theorem in one point or another, and it's very intuitive. First, before we get intuitive about it, I'm going to write it out in bland letters on the board. Okay, IVT. We suppose that f is continuous on the closed interval, that means including both endpoints, a to b. Okay? Let n, use a number n, be any number between f of a and f of b. Okay? Where f a does not equal f b. Then there exists a number c in the open interval a to b such that f of c equals n. What that means, what that whole function means, is that if we have a function, let me show this to you as quickly and simply as I can. We have a function right here, POW, coordinate plane, 0. Let me draw this bad boy here. Okay? There's our function. Y equals f of x. Here's point A, right there. Alright? Here's point B, right there. Okay? Here's our interval. And here is f of A, and up there That's f of b, because we can see it. So there we go. FB, B, FA, A. What this is saying is that we can find an n, we can find any number n in between here, any number between f of a and f of b. Let's pick one here. Now what that's saying is that there is some point c where f of x equals that number. We can just pick it. If n is here, well, then c is right here. If n is here, then c is here. If n is here, c right there, and here, c right there. That's what the intermediate value theorem says, is that anywhere between the outputs of f of a and fb, anywhere between there, we can pick an n, any number between, if this is 10 and this is 20, that any number between 10 and 20 there will be a c that will give us that number. That's what the intermediate value theorem says. And it's also the subject of today's big problem. So, today's big problem for continuity is the following. I love this one. A Tibetan monk leaves the monastery at 7 a.m. and takes his usual path to the top of the mountain, arriving at 7 p.m. The following morning, he starts at 7 a.m. and takes the same path back, arriving at the monastery at 7 p.m. Use the intermediate value theorem to show that there is a point on the path that the monk will cross at exactly the same time of day on both days. So go ahead, give it your best, and take care. Bye-bye. See you next time.